Good afternoon, everyone. I think we can start. Please take a seat and so good afternoon, everyone. Thank you very much for being here. It's really a great pleasure to have you here. So numerous for this Berni Alder Cecam Prize to Professor Giulia Galli from the University of Chicago. It's a great pleasure to open this afternoon, thanking you for coming, starting from the EPFL representatives, the EPFL President, Professor Anna von Kuberta in Morral, EPFL Vice President, Professor Ambrogio Fasoli, Deans of Faculty, Professor Paul Dyson, the Dean of Basic Science, colleagues from the Second Council, coming from many different countries, Taiwan, United States, Europe, many different countries in Europe, EPFL colleagues, EPFL students, and all the other who join us today for this ceremony. I don't take too much time because the afternoon is pretty dense. We have a lot of activities, including a mini workshop. Without any further delay or consideration, I leave immediately the stage to the EPFL President, Professor Anna von Kuberta in Morral, for welcoming you. And I take the opportunity to thank you again for being here. And thank you very much to all of you for attending and participating in this ceremony. Thank you.
Thank you, Andrea. Welcome to EPFL. It's nice to see this community coming from different countries. Originally, Cecam, the E in Cecam is European, and I think it was one of your vision to extend it to go abroad because we are a global community, and I think we see it here today. So welcome you all. So here we are gathering today as a part of a vibrant community advancing computational science and applying it to the most challenging problems in the world. And I think we will not run out of problems to solve. So saying a few words about Cecam. To promote fundamental research in advanced computational methods, fundamental research stays the base from which everything is built. Fundamental research, we shouldn't forget, even we like the applications, we like the progress, we shouldn't forget that fundamental research is what is at the origin of everything. And second, so applying them to applied problems, again, without forgetting that without fundamental questions, without asking questions that may come out of the blue, that are purely curiosity driven, we wouldn't be where we are today in science. So what makes Cecam unique, it's not only the scientific ambition, but the structure and support. Today, Cecam supports very proudly 29 institutions, around 14 European countries, and going beyond in China, Taiwan, United States. I'm not sure that there's many organizations that have all these countries together. And it's very important that today this is the case. So together, the partners do help define the strategy and guide the activities, ensuring that Cecam stays a collaborative and forward-looking organization. And I thank you for this. So if we take a few moments back to look at the history of Cecam, we see an evolution that is quite remarkable. First, originally the work centered in atomistic and molecular simulations, mainly between the physics and chemistry of condensed matter. But over the last five decades, the scope has expanded within material science, biology, medical chemistry, and contributed to major transformations. Simulation becoming today, I would say, the third way of doing science. It was more of a curiosity 50 years ago, mainly due to the small community, but also the computational means were much weaker than we have them today. Today is much more democratic, and this makes it very strong. And it will continue to evolve in the next few years. So today, your activities reflect frontiers such as multi-scale modeling, bridging quantum and continuum descriptions, as well as data-driven science, machine learning, artificial intelligence, the word that everybody talks about. So Cecam, you continue to adapt, to stay at the cutting edge, and you advance in understanding how complex systems evolve, which is complex systems is something that we need more and more if we look at the global challenges. So I think I am safe to say that Cecam continues to be ambitious in the mission. So with this, I think what you want to achieve is identify new directions for domestic and materials modeling, strive to inspire novel, innovative activities to foster international collaborations. This is not a detail. I think today we should concentrate on what we have in common to make sure that we pass all these crises and we evolve together for a better world. And in this sense, committed to transmit the values of Cecam, which is openness, rigor, creativity, and collaboration, and pass it to the next generations of scientists. I see there are several generations here, so passing it on. So it is with this spirit of excellence and inspiration that the prize comes here today, the Berni Alder Cecam Prize, which honors exceptional contributions to the field of that Cecam thought, and so several fields. And I will not say more words about the prize because after me, there's a person that will honor the prize awardee. So with this, I thank you for the invitation. Thank you for all being here. Thank you for bringing the field forward and for making this place a better world. And I give now the word to Stefan.
Yeah, thank you very much. Dear friends of Cecam here and abroad, let me join in the warm welcome of the previous speakers. And thank you for coming here and joining this event of the 2025 Berni Alder Cecam Award ceremony to Professor Giulia Galli from the University of Chicago. At first, I would like to take the opportunity to thank Professor Fontcoberta y Moral and Professor Ambrosio Fasoli for their constant support of Cecam, President and Vice President, and also the deans to supporting Cecam over a long period of time. Nothing is, the day we live in challenging time, nothing is for granted, and we are extremely happy to be part of such an exciting environment. Let me briefly introduce the Berni Alder Cecam Prize. The prize acknowledges, as already mentioned, exceptional contributions to individuals in the field of microscopic simulation of matter. The prize is given every 3 years. It has already a long history, a long tradition. It goes back to 1999. And the prize is named after Berni Alder, who studied in the end of the 50s by means of molecular dynamics, the phase transition of hard spheres, of matter of hard spheres. And he was probably the first who probably had fulfilled all the criteria to get this prize. Therefore, we named it after him. With this, with little more ado, I would like to open now the mini workshop, recent advances in computational material science, embracing the work of Giulia Galli. And after these 4 talks, we will move on to the prize ceremony, and the laudatio will be given by Kurt Kramer. Yeah. With this, let's start, and I hand over to Sarah.
So thank you very much, Stefan, for opening the dances together with the president of EPFL. My job is easier because this is where Cecam knows exactly what we are doing. This is when we talk about science and we celebrate the community that scientific endeavors can create. So we've organized a mini workshop, gathering what I consider to be a truly outstanding list of speakers, but also a community of speakers that belong in some sense to the scientific family that Giulia has contributed to create through her work, her teaching, and her collaborative network. So the 2 aspects, excellence in science and community, I think are well represented by what we are about to do. So we are lucky, we're going to have 4 talks. duration, speakers, is 15 minutes plus 5 for questions. Let's see what we can do. We have a lot of happy faces in the room. Very happy to see also young students. Please feel free to ask questions at the end of each talk. For those of you who are joining online, let us know that you do want to ask a question by raising your Zoom hand, and then you will be invited to unmute and be given the mic. Now, at Cecam, as you know, we like to keep things informal. Also, in the interest of time, I am not going to read the long list of scientific achievements of each one of our speakers. I'm just going to invite them to come here in sequence. The first one is Francesco Mauri from the University of Rome, La Sapienza, who will, I think, also tell us about his connection with Giulia.
Yeah. Thank you for the invitation. So I'm very glad to be here. Also, apparently, I'm the first PhD student of Giulia. Well, I was. I asked her for confirmation. I mean, my thesis was co-directed by Roberto Cari and by Giulia, but Giulia did something that I never did with any PhD student. So we were sitting side to side in front of a computer with a lot of frustration because nothing was working for years. And it was very depressing. And so, I mean, having Giulia on the side was a very extremely nice. I learned a lot of things. I learned not to surrender to difficulties, especially. So that it was, okay, already gave you another talk for another prize of Giulia, remembering that one of the engine of our collaboration was chocolate. And indeed, I was living in front of Blondel with a chocolatier in Rue de Bourg. And once a week, I was taking a piece of chocolate to eat with Giulia. So this morning, I went to Blondel. It's a little bit changed, but with an additional price. And also other things I was remembering is that basically I have Giulia for more than 2 years following my PhD, but then I think David arrived. And Giulia took 6 months. David or Manuel?
David is, because
no, he's the son of Giulia, right? And so Giulia took off, I don't know, 6 months, I don't remember. And I was really desperate. So my consumption of chocolate doubled or triplicated to afford the things. I was very happy when she came back after that pause. Okay, so that's my my memories, and yeah. So, and I think I never did something like this with any PhD student. I don't know how many of you had the enthusiasm of working side to side without stressing me, because usually there are cases. No, you didn't stress me as a PhD student, because if I sit on the side of one of my PhD students, most of the time, at the end, it gets crazy. So it was instead, it was a very pleasure situation to me. And so I missed in that period of suspension. Okay, that's about the so then you will tell me if a chocolate is as good as 30 years ago. Okay, so let's go to the scientific talk. So okay, I need yeah. So the pointer is here. So I decided to present this, which is this talk is the combination of 3 papers that we published this year. And the major engine of this talk is Alberto Guandalini, who has something in common with Giulia because he's from Modena, and actually he worked with me in Rome, but he spent a lot of time also in Modena because I think it's very hard to take out from Modena. And this is our outline. I will focus on the electron-phone interaction, on properties of graphene. Many of these type of effect has been studied in the field of strongly interacting system with a very model Hamiltonian, and show that it's possible to do it even from first principle, learning new things. And the So this is the things I want to show you. So this is the are some of the effects that arise from the fact that the electron interact in graphene. This is a plot of the Fermi velocity, so the group velocity of bands at the Fermi level as a function of doping. So with doping, the energy, Fermi energy changes, and the experiment are the points. And this is the result from a mean field theory. So actually, DFT is slightly smaller. And you see that basically the velocity diverges. So the effect is huge, is enormous. So it's hard to think that it can be treated perturbatively. Behind there is a theoretical work done, I think, with the renormalization group theory. And so it's interesting to see if we are able to reproduce these things from first principle. And the second example of interaction, here in the optical conductivity of graphene, if you have independent particle picture, we have this blue line. If you input electron-hole interaction, then we have a shift, but more important, we have a change of shape. So here the shape is changing, we have an asymmetric peak, and it's signature of an excitonic effect, even on a spectra of semi-metal. And what interests us the most are phonons, and these are the phonon dispersion in graphene, and here are the K points. And this is the DFT result, and this is something that we published a few years ago. The experiment are done on graphite and not on graphene, because it's not possible to measure with this accuracy graphene. And there is a big difference, and this big difference is the result of a renormalization of electron-phone interaction due to electron-electron interaction. Now, here you see that there is a divergence, and actually a divergence has been predicted to occur in graphene. This is graphite, but in graphene, that instead of having something like that, we could have a behavior similar to what is observed on the Fermi velocity. So our point is to see if you, first of all, you are able to reproduce these free data. I will not have time to focus on optical conductivity, so I will focus just on this other two. So what is the framework that we need? We need a framework that is able to describe electron-electron interaction, and in particular, the effect of screened exchange interaction, which is usually is taken care in ab initio calculation by GW calculation, and in the absorption data by Bethe-Salpeter equation. And the issue is that this theory is too hard to deal with at the level of precision that we need to reproduce this data on the energy scale of the data that I presented to you. And so we need to do a simplification, and the simplification is to use something that Giulia used a lot in the last year, so to use hybrid functionals, which somehow contain an interaction which is described in terms of a density-density matrix that is integrated over the screened Coulomb interaction. And Bethe-Salpeter basically use exactly this approach, because usually in Bethe-Salpeter we do a static approximation for the screening, which enter here. So here is the static screening. Instead, in GW, usually the screening is considered to be dynamic, but actually there is a way out, because as François Gigi showed many years ago, I think during perhaps his PhD thesis, if we consider DFT for the short range part, that is the only part that contains a lot of dynamical effect, the long chain part can be described with a static screening. So these are the structure of hybrid functionals. Usually in hybrid functional, W is taken as an empirical parameter, and what we do here instead, we compute W from the band structure itself. So we have a mixture of ab initio calculation of W and the use of a hybrid functional. And this is the reference of François Gigi, who basically put a theoretical foundation of what we are doing together. And okay, thanks to that, we only, instead of working with a green function like in GW, we can work with density matrix, which is a big simplification because we don't have a energy dependence, and that allow us to do a calculation numerically, where we do a second approximation, but we consider all these effects, the one related to the to this kind of term, which in Webban structure end up with this kind of term, so where we need the density matrix and W, just restricting ourselves to the important space of the low energy space, which is given by pi electrons. So what we do, we consider the one-body density matrix only between pi bands, and for that we use a time-banding Hamiltonian, and that allows us to arrive to this kind of k-point meshes, which are required if you want to describe the low energy point. So that it's impossible to do ab initio just because I need this kind of meshes to have the energy scale that is able to produce what I show you. Okay, so let's look to the band properties. Are we able? So these are the diagrams that we include, obviously, with the static W approximation, which are similar to the GW. These are the effect. These are the blue and red line are our two calculations. The blue line is the one where we ignore the fact that by changing the doping, we change the screening, and so we have to take into account this change. So we see that the effect is small, but the most striking thing is that what's happening if we use the screening from DFT. So if you use the DFT screening, we get something like that. Instead, the upper curve has been obtained by recomputing consistently the screening. So the effect of the screening increases a lot this rise, and due to the fact that the steepest are the band, so the less efficient is the screening. Now, let's go to the phonon. So how we do phonon? We look to the density-density response. So the density-density response, we compute density-density response within the scheme that I described you, which is this is the matrix, the tensor that relate the external potential to the induced density. If we know this object, we are able to compute phonons. How? We can just we have just to squeeze the density response with two external fields, and these two external fields are the one describing the phonon. So I can do the optical conductivity to get the middle curve, but if I put here the potential, the derivative of external potential with respect to the displacement of one atom S in the alpha direction and here on the atom T in the beta direction, then I can put here, I get this index are indicated which atom and which direction, and with this formula I can compute the phonon self-energy. And if I put that in invert defining green function with the spectral weight, I get the interacting phonon, including what? Including all things that I put in the density screening, and including the dynamical effect. Now let's look what's happening. So these are the phonon. The DFT1 are the one this dashed line, and this line are the phonon obtained with our approach. And you see that there is a divergence, and this divergence is more evident if we zoom that region. That is the zoom of that region. This is the K phonon, and then you see that I have that the phonon gets steeper and steeper, and if I compute the group velocity, this I compare the group velocity of these optical branches compared to the one of LA and TA phonon, and get that the speed of sound related to this excitation are 20 times faster than the one of acoustic phonon. So we get very dispersive. And then let's I zoom again. So I take this blue area and I zoom. In this case, in this area, what is the area where the electron at the Fermi surface of conducting graphene interact with phonons. So this is the only relevant part for the electron-phone interaction if I'm interested in transport. So it's a tiny spot, but it's all responsible for the resistivity in graphene. And if you look to that are what's happening to the phonon. That is the gamma phonon, and here is the K phonon. And this is the phonon dispersion, so I get the two kinks, and this is the phonon broadening. The phonon broadening is the inverse of lifetime. So tell me what the inverse time is the inverse of the time required for phonon to create an electron pair. So it's the reverse process of the conductivity where I am an electron that create changes momentum creating a phonon. So that is this process is the process responsible for transport, and this is the result of our calculation, whereas this is the DFT results. And so what does it mean? I have a factor of 5 of enhancement. This means that the electron-phonon interaction, and not the electron-phonon interaction, the electron-phonon scattering rate is increased by a factor of 5. And now, if we take a DFT, this phonon is already responsible, I think, for a room temperature for 30% of the resistivity in graphene. If this goes up by factor of 5, this means that all resistivity of graphene is just -4. So this means that instead of being graphene dominated by transport graphene dominated by acoustic phonon, as expected, the phonon which contributes the most to transport is the zone border phonon, but just if I take in account of this enhancement. I finish? No, I have 1 minute. Okay, now this is for the zone border phonon, so the phonon at the K point. Now let's look at the phonon at gamma. Here I compare the broadening of DFT with the one of our interacting picture, and here nothing changed. By magic, I keep the same number. Is magic or not? No, there is no magic. It's due to the fact that the phonon, the electron phonon at gamma is a gauge field. What does it mean? That the phonon at gamma, if I put a frozen phonon, I shift the Dirac cone laterally, and that this is the symmetry of the electron-phonon interaction, and this symmetry protects the electron-phonon interaction. And indeed, now I don't have time to explain you why, but so this means that I don't have an enhancement for gamma phonon because I have a gauge symmetry behind, whereas this symmetry is lacking at the K points, so I have this huge enhancement. And now, let me just finish that this is not at all trivial. Why? Because the electron-phonon interaction, so with full width of maximum, have an electron-phonon matrix element in the numerator and a square, two velocity in the denominator, which are the group and the phase velocity of electronic bands. And so what's happening is that this product is enhanced by a factor of 5. And for gamma phonon, also the numerator is enhanced by a factor of 5, so there is a perfect cancellation, and that is not by magic, but because there is a gauge symmetry. Whereas at the K point, I have that this is increased by a factor of 5, but this increased by a factor of 25, and at the end, I have 25 divided by 5, and the full half maximum is increased by a factor of 5, where this is not protected. So this tells me something very interesting, that it's not sufficient to compute the electron-phonon interaction, but I need to compute also the band normalization, because there are big cancellation between these two effects. For example, at gamma, there is a perfect cancellation of a factor of 5 on numerator and denominator. Now, I think I finish. So I don't know, I was in time, or do I have still?
For you, yes.
Okay. And these are the conclusions. So I put the free paper I was speaking from that present this result. I think the most nice result is that we change a little bit our picture, because everything is given by zone border phonon, and the other thing is that everything is controlled by the screening, because the screening enters in W, and so now I have something to work on to optimize the conductivity of graphene, because if I put a high dilated screening between graphene, I can decrease this electron-phonon interaction, so improve the conductivity of graphene. Okay, so that I finish.
We have, of course, time for questions, and Giulia.
I have at least two questions, but the first question is, what about the nuclear panel on the renormalization of the electron conduction?
But in this case are less important.
But how do you know?
Because we no, what do you mean of what?
So this, I mean,
On the electron phonon or on which property? So in principle, I can put also, so here if you want, we consider this vertex, I don't know. We consider this vertex correction. So you mean that what's happening if we put the electron phonon, a phonon here, not Coulombic interaction. This has been studied by Basco, and where in the paper that I cited in the beginning, where he compared it had or not the phonon, and the effect is minor compared to this. Is present, but is minor compared to this. I mean, as from what Basco obtained with a low energy Hamiltonian Dirac. But that can be included. So there are other effects which are relevant, that are the inclusion in this line, phonon, and that also in this case are small because it's a very clean system. Now, since you pose me something, I put a paper that you want to submit today, because that is an example where this effect instead is huge. So it is, oops, no, this is a paper that you want to submit today. This is a Lanthanio H10 superconductor in high pressure cell. So this is an experiment done in Anvil cell. This is a superconductor. This material is the hexagonal phase with 170 K superconductivity. And these are the phonon, experimental phonon, the points as a function of temperature. This is the superconducting gap. When the phonon enters here, so this phonon, for example, let's look to this. Here I have a jump of 100 centimeters minus 1 in a plateau of in a temperature range of 50 Kelvin. In 50 Kelvin, my phonon drop by 100, and from this, I can show that this is a superconductor, which is being put in doubt, but it's electron phonon superconductor. I can also measure the shape of a superconducting gap as a function of temperature, and this effect is something that goes is a phonon line on the electron propagation. And so these are the point, and this is the theory. And for this is theory for the, so the full line is the superconducting case where I open the gap, and the dotted line is the normal case. So this is a case where instead this effect is huge.
Okay, I would like to give time to one more question, if there is one from the audience. Not. Thank you so much, Jessica. It's my pleasure to invite to the podium our second speaker, who is Laura Gagliardi, who has traveled all the way from the University of Chicago to join this celebration. That I don't announce the titles of the talk because I don't know them. It is a surprise. Yeah. But start
Okay, great. So good afternoon, everybody. It's my pleasure to be here. Yes, it's true. I'm based in the US, but I actually come from Bologna, and you know, it's a pleasure to be in civilized Europe, and also to Well, it's not the United States, okay? That's enough. It's a pleasure to be here to celebrate my friend and colleague. I've always known of Giulia. She was like a star for me, a star at which I wanted to look. And our paths crossed later in years compared to the previous speakers. I've joined her as a colleague at the University of Chicago in 2020. And besides being a continuous scientific inspiration, we have also a lot of nice dinners with a lot of sparkling wine. And Giulia, congratulations, and to many more dinners. And this is a picture of we have also a joint student, and so she has been so inspirational that some of my research directions really evolved looking at her and her beautiful science. So this is the title of my talk. I'm a quantum chemist, and I like complicated electronic structure situations. And of course, in our work, we start from very small molecules. But ideally, if we want to look at the materials, for example, on which Giulia works as an expert, this is a metal organic framework. Okay, I know that for some reason, which has been awarded the Nobel Prize recently. So these systems have complicated electronic structure. The traditional methods for complicated electronic structure for so-called multi-configurational systems are very expensive. And so one of the goals of my group is to develop some of these methodologies, but for extended systems. And again, coming from quantum chemistry and a wave function, we work a lot with the concept of an active space. Probably I don't have to explain it to this audience of experts, but the idea, if one performs a complete active space calculation, this is a full CI in the active space. So over the years, there have been suggestions to break down this cost by, for example, dividing this active space in subspaces and setting up some rules for how the excitations can occur. My group and I have recently worked on this method called localized active space, and the idea is to put these full CI-like wave functions on different localized fragments of your extended system, trying to exploit the concept that electron correlation is local. And then we study different ways to recover the interfragment correlation. But ideally, this approach in this most primitive way scales exponentially only with each local active space, but ideally linearly with a number of fragments. So in quantum chemistry, these are good qualitative starting reference wave functions. But if one wants to be quantitative in energetics, one has to do something on top of that. Historically, people do perturbation theory. So you probably know about the CAS-PT2, NEV-PT2 methods. My group, in collaboration with Don Truller, this is a work that started about 10 years ago, have developed this method called multi-configuration pair density functional theory. So it's a form of density functional theory, but that starts from a multi-configuration wave function, CAS, RAS, GAS, and so on. And the idea is starting from this wave function, one can calculate the total pair density functional theory energy in one shot. So it's not like perturbation that you first compute CAS and then you do PT2. And here you see we have the classical Coulomb term and this, which we call a non-top energy functional. So the analogy with the Consham DFT is evident, but the difference here is that this is a functional of the let's see here, the one electron density and this on top pair density, which is a trace of the two body density matrix that comes from this MC wave function. So here both rho and pi come from the MC wave function. And so if what we express our energy as a sum of classical plus non-classical, where do we get the functional? And so what we have been doing so far is to borrow functional expressions from Consham DFT and translate them using this relation between the spin density, the total density, and the on-top pair density. So you see from here, you get R, chi, and so basically from the on-top pair density and the total density, one gets the spin densities and use this, for example, PB expression in analogy to Consham. And so these are some flavors of these functionals. So we have translated PBE, PB0, and this is the most recent meta version of the functional. So the idea here is that you pay the price for your multi-reference wave function upfront, but then the energy comes almost for free. And this method gives results, I will show you, analogous to NEV-PT2, CAS-PT2, but at a significantly reduced cost because you just pay the price for the upfront wave function. And so here you can see, for example, this is a benchmarking test for vertical excitations of organic systems, many multi-reference electronically excited states. And these are different basis sets, different active space sizes, and different number of systems considered, of excitations considered. And here you can see the mean absolute error. So if you do just CAS-SCF, it's not quantitative. NEV-PT2 is what the quantum chemistry community historically uses for this kind of problems. And these are our translated functionals, which give results similar to NEV-PT2, but the cost is only CAS-SCF. And going from CAS-SCF to NEV-PT2 implies having higher order density matrices. So sometimes, I mean, even if you can afford your CAS-SCF, you cannot afford the CAS-PT2 because of memory issues and time issues. So I want to say that we're not just looking at small, I mean, of course, we come from the molecule point of view, but we are now trying, for example, to exascale this method with these localized active active space wave functions. And we are looking at systems with rather large number of orbitals, and also the active spaces. These are not within reach of CAS-SCF. One can ask, what about DMRG? Yes, in principle, these are active spaces that can be done, but with DMRG, but DMRG has a lot of its technical issues. Here, in a way, the way in which you select the active space can be a little bit more controlled. And in principle, one can also do DMRG for the local fragment. So can we use MCP-DFT for dynamics? So to summarize, the advantages of this method is that it's as accurate as CAS-PT2, but it scales as the parent wave function. The disadvantages is that it's a single state method. It doesn't account for state interaction. It's in its initial formulation. And so it does not describe accurately, for example, conical intersection or avoided crossing. One needs a multi-state extension. And this is a typical case in which CAS-SCF describes this conical intersection, while MCP-DFT does not. So Matthew Hennefart has extended the method to a state interaction version. It's called linearized pair density functional theory. And this gives really good topologies now around conical intersections. And we can perform dynamics. This is just an example of the azomethane photoisomerization, in which basically we perform this on-the-fly electronic structure calculations with PySCF and Shark for the dynamics. But what I want to talk today about is the fact that I mean, sure, it's great, but it's still very expensive. And if we want to go to bigger systems, these methods are still too expensive. So can we eventually machine learn potentials, interatomic potential with these multi-reference methods? And this is actually, sorry, I apparently have a meeting. Let's just dismiss all. A a project on which we have been working in collaboration with the group of Michele Parinello. So Matthew, my students, Aniruddha, who is a joint student with Andrew Ferguson, who is very involved in the Cecam node in Chicago, and the Parinello group. And the reason is because, I mean, Michele has these beautiful papers in which he says that he solves all the problems in the world in catalysis using interatomic potentials, which have been machine learned on DFT. And DFT sometimes works, sometimes doesn't work. And here, I don't know why it's not going any, okay, I don't know what. Okay. So here I show you an example. This is the CH bond activation catalyzed by this species. And this is the rate determining step for which there is a rate constant measured experimentally. And you see, these are the multi-reference methods. This is B2 PLYP, which was chosen as the best functional for this study in this paper. But you see, these differences are important. So starting from this test case, we worked with a group of Michele to really do collective training data with active learning. And this is a typical active learning cycle if one starts from some Consham DFT data. But we use the MACE model. Of course, Gabor is here, so this is the best model in the world. But in principle, we are agnostic to the model. But this was good for a small set of data. This on-the-fly probability and unsampling developed by the Parinello group to really sample meaningful areas of the potential energy surface. And then there is this step, which is more challenging in multi-reference methods than in DFT, because we do not just need an energy and a force, we need also to choose an active space that is appropriate. So how do we do that? And in this case, Aniruddha and Matthew proposed this method, weighted active space selection protocol. This is the logo that they have invented. And the idea here is if you have to follow a reaction path, you have some information on a starting point where you have a geometry and a set of molecular orbitals and the final points. And now what about this geometry here? How can I select the orbitals so that I'm smooth on this surface? So in this weighted active space protocol, the idea is to select this, have this set of orbitals and select one with some, the orbitals of one with some distance constraint, average this weight on all the possible elements considered in this set, and then use this way to compute a new gas molecular orbital coefficient matrix for the new geometry. And then this will give at the end a set of MO coefficients that can be used for this intermediate geometry. So the idea here is if you just follow the traditional path, you would have molecular orbital coefficients at each point on this reaction. But if we instead with this weighted scheme, we just select the relevant ones, one ends up with these only 4 sets of molecular orbitals that will allow you to really follow the entire reaction pathway. And these are the 2 pathways with the traditional MCP-DFT and with this weighted protocol. And then so in a way, we have solved the problem of how to select an active space in a balanced way along a reaction. And then the active learning cycle can be performed. There is this extra step, which is a Parinello specialty to basically select the data in an efficient way, the data efficient selections. And so here I want to show you our final results. So here you can see this is the results of the dynamics from reactant to products. This is a transition state region. And what is important is that you really need dynamics for these types of reactions, because you don't have just a transition state, you have an ensemble of transition states. So this is a more realistic description of the process that is needed. And here you can see, okay, let's see, okay, of course it will not work, but no, this is the dynamics done with this machine machine learned potential trained exclusively on these multi-reference data. So the idea here is that we can have this pair density functional accuracy, so multi-reference accuracy, but we can perform simulations of the, for example, time scales of microsecond. And here you can see for one energy and force calculation, the whole time if you perform the traditional multi-reference calculation and if you perform this WASP MLIP calculation. And this is the time that is required even if instead of using multi-reference, you use DFT, so MACE trained on DFT data. So this is also an example of the cumulative probability for transition time distribution. So it shows that we can really model these types of time scales. So to summarize, with the WASP for active learning allows really to train this machine learned on multi-reference methods. It's possible to reduce the costs also by selecting the configurations that are important. And one can simulate bond breaking, bond forming for transition metal complexes with PDFT accuracy. So to finalize, I want to say that by coupling these methods with machine learning, we can treat, this is still a small problem, but we are looking at more extended systems. And as a conclusion, my point of view is that as machine learning continues to advance, it is precisely these multi-reference approaches, not DFT, that will define the next era of electronic structure. With that, I'd like to thank my group. You know, nowadays professors do strange things. I took them to a painting class. Don't ask me why, but that's what we do nowadays. And these are the three people who really worked on this project. And these are two previous group members, and these are the collaborators for the projects I talked about today. Thank you again, Giulia, and thank you all for your attention.
Very much. I must say I'm impressed by the science and by the painting capabilities of your group as well. The birds were beautiful. There is a trick.
Okay.
The talk is now open for questions. Okay, let's start with Michael, and then we go Nicola, and then we go Francesca.
I have a question about your WASP procedure. In particular, when you take the linear combination of these coefficients, how do you re-orthogonalize? Like what specific procedure do you use for that? Is because it's in the end, it's a question about how you retract on the manifold, right? You're basically following in a manifold of density matrices, and related to that, basically, have you looked at Grassmann extrapolation techniques or other related?
So,
3 questions.
So we use a Löwdin orthogonalization but in principle one could use other techniques. I can tell you the third answer is yes, this is a question that other people have posed about the Grassmann, and we are looking into that. It will be the next step. And the second one, I forgot. Sorry, there was a second. Okay, all right.
It's basically the answers are complete.
All right. Okay.
I think Löwdin is a good choice, actually. And I can give you a more mathematical reason at some point.
Okay. Well, I'm glad that I passed this quiz. All right.
All of us straight on math.
Okay.
Thanks, Laura. Very, very beautiful. I mean, one thing, especially with all these multi-reference systems, you can have, of course, different multiplets, and you can have chemical reactions that are exothermic but have low reaction rates because you need to change the spin and so on. So, if you want, the question is, how do you deal in a machine learning model with the fact that for a given atomic configuration, you might have multiple multiplets, and some might become relevant as the reaction progresses?
So if I understand, it's more talking about not just doing it on one electronic state, which is the ground state, but also excited states. Yes, so that's, yes, so that's what we are studying at the moment. So if you do the traditional quantum chemistry calculation, okay, we can do it within the active space framework. Of course, you need to compute the coupling matrix elements appropriately. It can be done for small molecules. With the machine learning, I think there is a lot of work going on in terms of trying to machine learn the dynamics of excited states. And I think one of the problems is, again, the coupling. So if you have different spins, I think it's easier than if you have same spin multiplicity for the coupling. So it's ongoing project, and it's not going to be as simple as doing just one state.
Is there any hope to arrive to solids?
So, okay, so we have if we do the traditional quantum chemistry, we have this localized active space PDFT, which has periodic boundary conditions. So basically, each unit cell is represented by one of these wave functions. And then, for example, you can describe charge transfer or electronic excitations by these wave functions. In principle, so the problem is at the moment we can do only energy calculations. Doing gradients in this periodic environment would be more challenging, but in principle, yes, that's what we're trying to look into.
So there are no questions.
I have a question, a side question. You showed during your talk some molecules. And one was chromium-2, the other one was iron nickel, and so on. I assume they represent quantum spin systems.
Yes.
And can you probably calculate also, so basically these are quantum spin Hamiltonians at the end, which describe this magnetic interaction. And probably you can calculate from this also the interaction parameters.
Yes. So
basically, you can calculate these interaction parameters with your two different approximations, and you can calculate with DFT.
Yes.
And I would like to ask you, how does it compare?
I mean, I think the problem is that if you want to compute these magnetic parameters, you have to take into account many electronic states, not just the ground state. And they're very close in energy, these states. So I think that's where DFT sometimes has a problem there, because there are many close-lying electronic states.
I'm aware of the problems, but I would like to know how much of a problem it is. So if I compare, by knowing how good you are, how much it is, does it compare?
I mean, I guess it varies a lot from case to case. So I think that in general, it's a problem in Concham DFT. For example, this iron 4 sulfur, it's really, and so if, let's say, the magnetic centers are not too strongly entangled among themselves, maybe Concham DFT can do a reasonable job. But I think that when there is more correlation, so I don't have a quantitative answer, because sometimes again, it varies from case to case, I would like to say, yeah. And again, in Concham, which functional do you use?
There's a fundamental problem, because your systems are not spin 1/2. Your systems are spin 1, spin 2. And then the question is whether our functional, whatever it is expressing this aspect well enough and good enough. For the first term, asymptote, you get the right answer in DFT, but maybe beyond that. Yeah.
So I think this is a super conversation. Maybe we can continue this over a glass of champagne during the aperitif.
Okay.
And maybe, Laura can provide some benchmark data that
Yeah,
would be
yeah.
fun to compare with what you have in mind, Stephanie. So thank you
Thank
again.
you so much.
And our next speaker is Marco Govone from the University of Modena and Reggio Emilia. Already, I think that there is a resonance with Giulia, and Marco will probably tell us.
Thank you. Okay. Here. All right, thanks for the invitation and congratulations, Giulia. Yes, I'm from Modena. I have to disclose this. Yeah, I knew that you would have said that. I'm actually from a small town, half an hour away from Modena, and Giulia always reminds me that every time I say I'm from Modena. This title, I hope you remember this title, Giulia. This is actually from one of your talks, the electric response of molecular and condensed system from ab initio simulation. Indeed, I want to convey to you how a source of inspiration Giulia was for me and for all the students and postdocs that work for her, with her. So I would like to reset the time to 2010, to this Spring College of Computational Nanoscience that were organized by Nicola Marzari is here in the room. Thanks also to the support of Cecam. It was in Trieste. I was a graduate student. I was working on nanostructures, so this seemed to me like a good choice to learn something new. One of the lecturers was indeed Giulia Galli, and this is the day we met, Giulia. Yes, 2010, and this is the title of your talk. And the slides are online. You were talking about optical properties of silicon nanocrystals, and I was working with silicon nanocrystals. I was interested in computing Gaussian, current multiplication. Then you went on discussing realistic environments for nanostructures, and you gave a beautiful lecture about predictive modeling of multiple properties with controllable accuracy. This slide took really, I felt this point in your slide, because you were discussing how to compute dielectric matrices in a better way. So the equation on the top is also what I was using for my research as a graduate student. And it's an equation written in plane waves to compute the dielectric matrix with the random phase approximation, Adler and Weiser, that we know from many decades. And you were saying, well, if you apply this directly, straightforwardly, it may be prohibitive for large systems. And indeed, I was struggling during my PhD to apply this formula to large nanostructures. And so you proposed a new method to compute dielectric matrices using perturbation theory and to compute actually eigenvectors and eigenvalues of these matrices, something that I never thought about. And you had these preliminary papers published in a few years before this college. And a few years later and a few letters of recommendation later, I joined your group as a postdoctoral scholar, and I managed to found this plot that we looked at for many afternoons together. So this is an analysis of the dielectric eigenmodes, so the eigenvectors of the dielectric matrix in a silicon nitride interface, solid amorphous interface. We have a real space plot, so plot in real space, and also Fourier space, where we see that all the response is confined to the first 5, 8 Rydbergs, although the simulation was done with 8 Rydbergs. And there are the eigenvalues that are dropping towards 0. And this is what motivated us to look at ways to describe the dielectric matrix and the W, the screen-Coulomb interaction, in a different way. So with the Hartree-Fock, the Baire-Coulomb interaction, when you expand it in plane waves, is a diagonal matrix. You don't couple plane waves with different wave vector. With the screen-Coulomb interaction that is at the heart of GW, and as we will see in the next slides, also of Betz-Salpeter, of hybrid functionals, and also on quantum embedding, it's a full matrix. So it's a matrix that it's dense, and for a large system, you may not be able to store 8 Rydbergs of this matrix. And so this is what Giulia was saying. And for me, the full matrix is like Flemish art, when all details are important, right? And now with Giulia, we became impressionists. Like we capture only the key features of this matrix. We retain only the principal components by achieving a low rank decomposition. So we sacrifice all the details to convey the same impression of the matrix and of the physics involved. So we apply this to the calculation of quasi-particle energies in the GW approximation. We eliminated summation over empty states that was using density function perturbation theory. We showed that the number of eigenvectors of the dielectric matrix controls the accuracy of the method. This was implemented in a parallel way and also with full frequency integration. And this was the initial concept behind the open source software West for the calculation of excited states. Thanks to this, we were able to do the silicon-silicon nitride interface, the studied band offsets, band gaps of all sorts of nanoparticles, even ones having two compounds. Defects in materials. This is at the bottom is localized density of state. We have spin defects in blue and in red, whether they if they have spin up or spin down. You can see that thanks to these advances, both on the method and on the code part, we were able to simulate tens of thousands of electrons, and this is what really we needed in order to simulate complex heterogeneous systems. So we expanded this to eco solutions, where we also had to use the electric properties to develop new hybrid functionals. We studied the photoluminescence, the photoelectron spectrum of eco solution, as well as of surfaces with oxygen vacancies. We applied it to solid liquid interfaces now that we were able to do many simulations with several thousands of electrons. And later on to defects in 3D and 2D materials. And indeed, here in this field, this was motivated by quantum technologies, and optically active spin defects in semiconductors are actually interesting because they are qubits in a solid state system that can be initialized and read out with light. So this is why it's optical. They operate at room temperature, and they have application in quantum sensing and quantum computing. And one of the prototypical examples for this is the nitrogen vacancy center in diamond. So here you have optics, so no longer photoelectrons. So when you excite your electron, the electron remains in your system, and therefore GW was not enough. We had to expand this to Bethe-Salpeter, TDDFT, and Bethe-Salpeter. So computational challenges for this is to first study the excitation, vertical excitation, where the potential energy surface can be multi-configurational, and then optimize the position of the atoms by computing forces for excited states, and then eventually also describe the hopping between surfaces to simulate the optical cycle. And this was needed in order to simulate photoluminescence. And of course, for many of these calculations, the concept behind the electric matrix are very important. So for the simulation of vertical excitations, in any code, we can utilize the delta CF method, although it is unjustified and numerically unstable. So what do? You simply constrain your occupations to promote an electron from occupied to unoccupied states, and you hope that this the numerical solution goes well. A better way to solve this problem is to use TDDFT and the Bethe-Salpeter equation, typically with Cassida solvers. And what we have done with Giulia is to extend this to the case of density matrix perturbation theory, where we could use the sparsity of the density matrix to really speed up the calculations. Indeed, now, at that point, we were able to simulate systems with thousands of atoms at the level of Bethe-Salpeter. This is actually very important because we want to have a defect in the dilute limit. So with enough diamond atoms surrounding the defect so that the defect is in the dilute limit. So the convergence as a function of the size of the simulation box is quite trivial for the ambient center in diamond, but it's not trivial for all defects. And indeed, we can track now the convergence, for instance, of silicon vacancy in diamond and also bound excitons. And we can also do, now that we achieved, we can apply the Betz-Salpeter equation to system with 1700 atoms. We can also study point defects interface with line defects. This was the case of a dislocation in diamond. And you can see that on a GPU cluster, this calculation takes a few minutes, thanks to the method developed. If you want to go beyond an expansion over single excitation, you want to include also double, triple, and in principle, all the excitation, full configuration interaction, you would like to start from density functional theory, which is an approximate way of solving the Schrödinger equation, and get to the full configuration interaction, which is scales factorially. So you cannot apply to the full system, but only to a fraction of your system. So we developed the an embedding scheme, full configuration in DFT, where we define an active space, find an effective Hamiltonian, and then find the ground and excited states. And in defining the effective Hamiltonian, the concept that we saw before about the dielectric matrix are really important, because the way the electrons interact is through a constrained RPA approximation, which means that we have an effective interaction between the electrons belonging to the active space, which is screened by all the other electrons that are not part of the active space. And the double counting term requires also a formulation of GW on top of DFT in order to be exact. Now that you have all these theories within the same code, you can start to make a really fair comparison between them, and because you can control the numerical techniques, for instance, for diagonalization, because they are the same across all methods. And you can really ask yourself, what is the importance of double excitation and other questions that are relevant. For forces, so we wanted to compute the gradients of the energies, and we utilized a formulation developed by Hutter 20 years ago. And we extended Lagrangian formalism that we generalized to the case of spin flip excitation. So now we were able to optimize the atomic positions in a triplet or a singlet excited states. And we verified this by simulating the vibrationally solved absorption spectrum for singlet to singlet transition in the nitrogen vacancy center in diamond. Finally, we closed the loop and we could simulate intersystem crossing rates for hopping between triplet and singlet states, which is quite impressive, in my opinion. So codes used quantum espresso to solve for the density functional theory, the single particle orbitals, and then West, the code that we developed over the years for excited state calculations. The code is interfaced actually also with other electronic structure codes, QBox, PySCF, and with TensorFlow and Qiskit frameworks. It is open source. There are tutorials, and we are connected to the community. The code scales well on GPUs. All the features, embedding, Betz-Salpeter, TDFT, forces, GW, scale well on GPUs. And we decided to look also at the possible calculation done on GPUs and also QPUs, quantum computers, where we solved for the quantum embedding problems using a mapping to qubit Hamiltonian with a qubit efficient encoding, a hardware efficient ansatz, and an error mitigation technique. The result is that we can solve the quantum embedding at the level of accuracy that is the same that one has by solving this workflow on a GPU. A conclusion, so I only talked about how important, how relevant were the ideas pushed by Giulia in 2010 and then developed over the years for the optical properties. But if you want to accelerate, for instance, the search for stable defects using ab initio methods, then you need to look at many other properties, and Giulia really pushed the envelope for all these, the calculation of all these properties. Finally, so I could not list here all the collaborators. It was impossible. So I decided to put no name at all. I would like to thank you on behalf of all your students and postdocs and collaborators, Giulia, for inspiring us, and I congratulate you for this well-deserved prize. Yeah.
Very, very nice talk, which is now open for questions.
I have a question, but I will.
Let's see. I think you can go and inspire other people to ask questions.
I have a question that is both for you and Laura, in a way, and I know we talked about this many, many times. So we have a problem in determining the active space. And we also have a problem in optimizing the active. I'm sorry, I'm talking about quantum embedding. And especially, I mean, we have partially solved the problem of project. So are there techniques that have been, for example, developed for LAS and other framework that we could apply here?
I think the question was more for you.
I mean, based on all the discussion, I mean, what is your take?
I think we haven't solved fully the problem on the choice of active space, although we made progress in the last paper. But I cannot, I don't know, maybe.
From what I understand, in your case, you tend to select mainly doubly occupied, right? Very few virtual.
No, but no, we do have virtual. And
That's where the problem.
Yeah, this is where the problem comes. But for the selection all of the occupied, this is a little bit technical. I will stop. But
I mean, I find it hard to stop you today.
yeah, but we have a problem in optimize the choice of space. So I think I don't know. Maybe there are ways of.
No, it is. I gave a talk recently. I said that my students say you really exploit our brain. You put us 6 months, and we have to spend 6 months to find an active space for a molecule. Do you think it's fair? And that's why. So no, sorry, I was about to make a joke. But so no, it requires. So in principle, what we are trying to do is to learn all the rules that the human and try to make it more automatic, or at least have a little robot that tells you this is level 0. Then the human can come to try to refine level 0 to level 1. Yes.
Yeah. Maybe we could think on this one.
Sounds like a wonderful topic for a workshop. Do we have more questions?
Well, if you confirm it is very difficult to find active space. And for example, if you see this model up there, it's like a kind of a mini body model, in which you can do field calculations, you can do of this interactions and things like that. They are very different from the original ab initio calculator. And if you think about your Western world quantum algorithms, everything is milli-EV.
Yes.
On that sombering note.
Okay.
No, seriously, are there more questions online or in the room?
I want to ask about the functional choice. I mean, you have a lot of experience, so how has your approach evolved over years? I mean, do you need to use hybrid functionals or that way with GBA?
So typically we start from PBE and then we go towards hybrid functional based on PBE, but I think that include a fraction of exact exchange for cases where the of need. So when the density is not well described, is not well localized, and so there are, for instance, for all the system with water and all oxides, we go there. We consider hybrid functionals. Yeah.
Okay,
Okay.
thank you, Marco.
Thank you, Giulia. Thank you.
Now, our last speaker for this mini workshop is Davide Donadio from University of California, Davis. You may realize that this is not Davide, right? This is Bogdan Nikita, our IT manager at Cecam. Davide was on his way to this workshop, but his plane broke twice, fortunately, before taking off from Chicago, so he couldn't make it. However, he really wanted to be with us, at least in spirit, and so he has sent us a recording of the talk that he would have given, and that's what we're going to step into next. I don't think the questions will be possible, but let's see how we go. Or no answers, right?
Hello, everybody. Even though I have been, I'm stuck in Chicago because of an airplane problem, I would like to contribute to the celebration of Giulia Galli's Berni Alder's Prize. And through that, I want to do it through a presentation that is highlighting Giulia's impact on the field of molecular simulation of heat transport, and that impact is the impact that this work that we started together has had on my career as well. So I joined Giulia's group in 2007. The group was relatively small. She had just joined UC Davis for about a year. We were about 6 happy postdocs enjoying science in Davis and the beauty of California. Just a couple of years later, the group was much larger. We had several successful graduate students, more postdocs, and also some little additions here. And as you can see from Giulia's family, we were definitely enjoying life. So I distinctly remember when I joined the group, first meeting I had with Giulia, she had a whiteboard with a list of projects, and she was like, well, pick one. And I didn't know about this infamous quote by Rudolf Peierls about the difficulties of heat transport. And there was a project on simulating heat transport in silicon nanowires. And since I didn't know anything about it, I thought it was an interesting challenge, and I just took it up. The reason why we wanted to study heat transport in silicon nanowires was to use these systems as thermoelectric, so exploiting the good properties, the good electronic properties of silicon with a high Seebeck coefficient and a high conductivity that can be tuned by doping. But the problem with silicon for a thermoelectric application is that it has a high thermal conductivity, and that limits the value of the figure of merit CT. So the idea was to engineer silicon to become a phonon glass, so a thermal resist insulator, and keeping its good electronic properties as an electron crystal. Other reasons why it's interesting to study thermal transport is certainly for thermal management, for example, in electronics, where half of the power of data centers goes into cooling, in batteries and thermal barrier coating and other energy harvesting and conversion systems. The tools we had at the time we wanted to work with at the time was molecular dynamics, and there were two options. There are two options if you want to study heat transport with molecular dynamics. One is to use non-equilibrium molecular dynamics and basically apply directly Fourier law by heating a part of your simulation model, cooling another part of the simulation model, setting up a steady flow, and then obtaining the thermal conductivity from the temperature gradient. On the other side, one can use equilibrium molecular dynamics and the Green-Kubo formula. So basically exploiting the fluctuation dissipation theorem, and the Green-Kubo formula links the heat current to the transport coefficient through the correlation function and the integral of the correlation function. Both approaches have serious issues with time and size convergence. It's explicitly written here in the Green-Kubo formula. In the non-equilibrium case, you need the time to get a stationary heat current, and the size problem is quite serious because the heat carriers are limited in the space they can travel. The mean free path of the heat carriers is limited between from the distance between the hot and the cold reservoir. So one has to extrapolate the thermal conductivity. Another problem in the Green-Kubo formula here is worth mentioning is the definition of the heat current, because the explicit calculation as time derivative of the energy density is not trivial for many body potentials, and even less so for in the case of quantum simulations with density functional theory. And the problem has been brilliantly solved by Stefano Baroni's group about 10 years ago. Somewhat, it only inspired by discussion with Giulia herself. So we're back in March 2007. I had coded the molecular dynamics approaches in a custom-made molecular dynamics code. And Giulia told me, well, let's start with a simple system. Let's do carbon nanotubes, because carbon nanotubes are a well-defined system, not too many atoms, and so it's easier than silicon nanowires. Well, this was somewhat a misjudgment, because carbon nanotubes are as far as from simple as it can be. So this is a collection of 20 years of molecular dynamics simulations, some non-equilibrium, some equilibrium molecular dynamics. Certainly there is no consensus of the value of the thermal conductivity of a carbon nanotube at a given temperature. There is not even consensus whether it is finite or not. So typically non-equilibrium methods show that the thermal conductivity diverges, and equilibrium simulations seem to suggest that it converges. Experiments seems to are a bit all over the place. For example, this group in Taiwan, Chiwei Chan's group, claims that they observe divergent thermal conductivity in millimeter-long carbon nanotubes. But if this is the evidence, that's, as I said, a little bit all over the place. And the reason why one may think that the thermal conductivity of carbon nanotubes may diverge is that since the carbon nanotube is the closest possible thing to a 1D system, and in ideal 1D systems like the Fermi-Pasta-Ulam model, thermal conductivity has been proven to diverge like the power, alpha power of the length. So we tackled this problem with molecular dynamics. We were very careful at studying size convergence and convergence. The length of the simulation, you need several nanoseconds to converge the integral of the correlation function, and many repetitions of the simulations to sample the phase space properly. So we find that the thermal conductivity converges also for not too large system sizes. Around 50 nanometer long periodic nanotube is enough to get the well-converged thermal conductivity. Went all the way to 200 here. Another thing we found is that when you deposit the nanotube on a substrate, the thermal conductivity is largely reduced, which shows that, well, it's a rather delicate property. So basically there is an interference of the substrate with the heat carrying modes of the nanotube. At the time, we were quite satisfied with that work, and we moved on to the nanowires. But more recently, I have kept on working on carbon nanotubes, repeated the equilibrium and simulations with more efficient codes, more longer simulations, etc. We got pretty much the same results as back in 2007 when I did it with Giulia. And what we added in this work was the non-equilibrium simulations very systematically, all the way to 10 micrometer long carbon nanotubes. That's a very large system. So at this point here, what we find here from the non-equilibrium simulation is that thermal conductivity never exceeds that of equilibrium simulation, at least for the length that we could study. Of course, we cannot compare directly molecular dynamics to experiments because in real life, phonon populations are quantum mechanical and molecular dynamics is classical. So we resorted to lattice dynamics to obtain a better understanding of this system and then eventually go quantum. And in lattice dynamics, you basically solve the Boltzmann transport equation that is written here using the harmonic properties of the system and the anharmonic, the first order anharmonic property, that is the 3-phonon scattering term that is contained in this scattering tensor. So you basically have to invert the scattering tensor, you get the phonon mean free paths and the thermal conductivity through the standard kinetic equation. The problem in a finite size system, that is what we wanted to study, is that typically people apply Matthiesen rule, and that is done a posteriori after calculating the intrinsic phonon mean free paths that are here. You apply a correction introducing the boundary scattering, and you get the phonon mean free path for the system. So this does not agree at all with the molecular dynamics simulations. And the reason is that it's a relatively poor approximation. It's a coarse approximation. You need to do things a little better. It's not very difficult because we found out that applying the McKelvey-Shockley approach, the proper way to introduce boundary scattering is a diagonal term, is a diagonal add-on to the scattering tensor, and then only after that you invert it. When you do that, you get a very good agreement between lattice dynamics and molecular dynamics. Now, the question whether the extrapolation of the lattice dynamics exceeds the EMD limit, that is probably due to the fact that we are considering only third order anharmonic. So sorry, 3-phonon scattering, so the first anharmonic order. Well, now we have a lattice dynamics model, and we can run it with quantum populations, so we can compare directly to experiments. We actually get substantially good agreement with Chiuei's experiments. We had thermal conductivities in the about 10,000 watt-meter Kelvin at room temperature for millimeter long nanotubes. We can also do a breakdown of the contributions of the various modes, and here we find that the two acoustic modes, two linear acoustic modes, the longitudinal one and the torsional one, are the main contributors to the thermal conductivity of the system, whereas the flexural modes, that are these quadratic modes, are the main scattering channels. And these modes are those who keep the thermal conductivity non-divergent in carbon nanotubes. Now, going back to the real problem that was transporting silicon nanostructures, the reason why we thought, or the community thought that silicon nanostructures, in particular silicon nanowires, would be good thermoelectric was that two works back-to-back in Nature reported a major reduction of the thermal conductivities of this system from the bulk value of 160 down to around 4 watt-meter Kelvin. Now, the question was, what is the reason why we have such a large thermal conductivity reduction? Is it phonon confinement, or is it due to surface effects like this disorder surface? Of course, we couldn't simulate so thick nanotubes. The ones in the image before were 200 nanometer thick. We do a couple of nanometer thick here, from 1 to 3. And what we see is definitely that it is the rough surface that controls the thermal conductivity, because dimensionality reduction alone does not reduce the thermal conductivity significantly with respect to the bulk. Here I'm plotting the reduction as the fraction between the bulk thermal conductivity and the thermal conductivity of the wire. Like a square section with some surface disorder is more effective in reducing the thermal conductivity, but even more effective is surface amorphization. So we have a couple of layers of amorphous silicon at the surface of the silicon nanotube is enough to reduce the thermal conductivity to that of bulk amorphous silicon, so 100 times lower than that of the bulk. Now, to understand this problem, we were again applying the Boltzmann transport equation with mean-free paths calculated directly from molecular dynamics. And the results from this approach that are in the graph art, this black triangle, are in very good agreement with the direct MD simulations for the crystalline system, but they don't account for the full thermal conductivity of the core crystalline core amorphous shell nanowire. Now, to account for that, we had to include, we found out that we need to include a term that is this diffusive term that comes from the theory of heat transport in amorphous materials, in glasses, and that was developed by Allen and Feldman in the late 80s and early 90s. Now, with this term that kicks in when modes are not propagating anymore, so they don't provide a contribution through the standard kinetic expression. With this term, we obtain an excellent agreement with molecular dynamics. Now, this theory, this model is somewhat heuristic, and only about 10 years after, I was contacted by
Someone in the room contacted.
Let me refresh.
Oh, yeah, he did. It's.
And the Wi-Fi.
Yeah. No, it's not. Wait.
Yeah.
Hello, everybody. Even though I don't account for the full thermal conductivity of the core, modes are not propagating anymore, so they don't provide a contribution through the standard kinetic expression. With this term, we obtain an excellent agreement with molecular dynamics. Now, this theory, this model is somewhat heuristic, and only about 10 years after, I was contacted by Stefano, and we worked together on a more basically analytical demonstration that the theory was actually that idea was actually solid. So Leila Isaeva and Stefano Baroni had the idea of introducing the harmonic heat current expression from Hardy into the Green Kubo integral, and they obtained an expression for the thermal conductivity that looks a lot like the kinetic theory. We have the heat capacity, some objects that have the dimension of group velocities and a relaxation time. But for different polarization NNM at the polarization index, these generalized group velocities have the form of the Allen and Feldman diffusivities. Now, you put together with the Lorentzian wheel, and you have a model where the diagonal terms, the n equal m terms of this sum, are the propagating modes, and the off-diagonal terms give the diffusive contribution. And curiously, these equations were obtained starting from a completely different approach by Michele Simoncelli, Francesco Mauri, and Nicola Marzari. Pretty much a few months, they published a few months earlier than us, but pretty much we were working at the same time on that. Now, this story about the effect of disordered surfaces on the thermal conductivity of materials has accompanied me in the follow-up of my career after leaving Davis. When I was at the Max Planck in Mainz, I was working with experimentalists from Finland and Spain. That's Crivia Sotomayor Torres group and Giulia Opelto group, where they had experiments on silicon membranes. So these are crystalline silicon membrane. You can see it from the TM image. And there is a substantial reduction, which the black dots, of thermal conductivity as the silicon membranes get thin. So we had the occasion to work at the same scale as the experimentalists. And we did the same type of modeling as for the nanowires. So we simulated perfectly crystalline surfaces, not substantial reduction in thermal conductivity here. We introduced some roughness at the surface, and we have a reduction of thermal conductivity, not enough to get into the experimental ballpark. And then we simulated the amorphous layer, and that got us exactly on top of the experiments. The experimenters were so excited that they were etching out, these are experimental data, they etched out the oxide layer from the membrane at 10 nanometer, and they saw an increase of thermal conductivity that was getting in the same ballpark as our rough membranes. Now, well, what I want to convey here is certainly that Giulia has had a great impact on the field of molecular simulation of heat transport. That's had also a major impact on my evolution as a scientist through lessons that I learned working with her. And this is what pretty much I have learned. The most important one is that one must keep having fun doing science. And I want to thank you all for your attention, and thank Giulia for all your inspiring contribution to our community.
It's really a pity that Davide cannot be with us to celebrate, but let's all make sure to convey to him how grateful we are for, providing a contribution in spite of all odds. Now, this concludes the mini workshop part of the afternoon, and I would like to invite Kurt Kremer, who is the recipient of the 2022 Berni J. Alder Cecam Prize, and who will be the master of ceremonies for the next hour or so. Thank you, Kurt.
Yeah, thank you very much. For me, it's a great pleasure and a great honor to be here and to be able to present this award to Giulia Galli. But I want to say something before I say a little more about her. I'm very happy to see that many people are here. I remember 3 years ago, we all suffered from COVID, and it looked quite different. So I'm really happy to see you all here, that we can celebrate this. And I'm not only happy to be here, not only happy that you are all here. I think also Giulia deserves this, that you are all here. Yeah, let me introduce her, and I don't know whether I need to do that when looking at the people and the people who gave the talks here. Giulia Galli is for you a family professor of electronic structure and simulations in the Blitzko School of Molecular Engineering, professor in the Department of Chemistry at the University of Chicago, and director of a Midwest Center for Computational Materials at Argonne National Labs. That already tells us that what she is doing has impact and effect on much more than of what just a typical professor of physics or chemistry would do. Her impact is much wider, her influence is much wider, and her interactions certainly also are spreading in a much wider area. Before she came to Chicago, she also made a typical but very considerable and remarkable career. She got her PhD at Cecam in Trieste, I think a place where many excellent scientists came from over the many years, and then moved on as a postdoc to Urbana, Illinois, and the IBM Zurich, also places very well known to everybody in science. And after that, she got her first own group at EPFL here in Lausanne, where she spent several years. And then in the late 90s, and then at Lawrence Livermore National Lab in the US. From that, she moved on to become professor at UC Davis, where you also worked with Davide, one of your mentees who made his way. And I must say, I enjoyed very much working with him when he was in Mainz at our institute. And from where on you moved then in 2013 to Chicago, to this first of the Pritzker Institute of Molecular Engineering, which I think is a perfect environment for somebody like Giulia Galli with that broad interests in understanding materials and doing something with these materials, not just understanding these materials. Of course, this was recognized also by other institutions, and I don't want to list the distinctions or all the distinctions you got. I only would like to mention that in 2020 you were elected to become member of a National Academy of Sciences in the United States. And looking into the websites of the National Academy of Sciences, one can see what Giulia really stands for and what she is recognized for. And she is recognized for the development and use of theoretical and computational methods to understand and predict properties of solids, liquids, and nanostructures at the atomistic level from first principles. So not only crystals, but also liquids, nanostructures, disordered systems, and so on. And then it goes on that she contributed significantly to method development of first principles, MD, and so on and so on. And extended this interest also to other areas of research, which now recently also more included quantum information science. But let's be a little more specific. When you look at the publications, you go through the publication list, of course, you see that she is highly recognized and highly cited. But when you look then at the papers, let me start with the one which is most cited, that is sticking out there. What you see is, and that is a paper from 2010 on emerging photoluminescence in monolayer molybdenum sulfide, you see that she's very much interested in systems where you have specific boundary conditions which made it more complicated, like confinement, surfaces, and what Davide said, nanowires, and so on and so on. And that's, of course, where you get much closer to the reality, to experiments, and you do not stick, and she does not stick to the simple, quote unquote, simple idealized systems. And there I realized also that very recently you had a paper on polymerized tile acceptors. So you are slowly going into soft matter. That's very nice. Coming from the Max Planck Institute for Polymers Research, I think that is very nice, because there in organic electronics, we have for many, many years this problem that local conformation and packing directly affect the properties. On the other hand, you have systems which are much more easy to process compared to many hard matter systems, but you have to control the processing in a very different way. And where these studies are extremely important. So I'm looking forward to see more in this direction as well. Yeah, I know. And there are many other works which are extremely important, and it really integrates more and more science and experiments, and recently also with molecular engineering, which I think is an extremely important aspect. Typically, engineering classically are big systems, big machines, and so on. But what we have to do is we have to control what is going on a microscopic scale, on a molecular scale. And not only from what these systems do afterwards, but especially from the way we get there. The molecular processing is one of the really, I think, grand challenges of our days. And there I think Giulia made many important contributions and does a lot with her group and people working with her. And then what is mentioned, but where I'm not an expert at all, is order of n scaling algorithms for electronic structure DFT calculations, which really found many applications. The first principles, MD for spectroscopy of liquids and so on, and other systems. Then the coupling of first principles, MD, and many body perturbation theory, which became a kind of important central part for these GW Green's functions methods for energy calculations. And so, and one could go on and one could go on. I don't want to do this here, but I think it's clear that her impact there was huge, and many people benefited from this work. And many people also means that you had many former students and mentees who made their way in science and technology. And one, we had talks by several of them. And as I said already, with one I had the pleasure to interact for a number of years as well. So I have to make it short. I'm asked to be short, and I think I should do this after these talks. I think Giulia Galli really is a leader in the field with enormous impact, and highly respected by colleagues and students, not only for the work she is doing, but also the way she interacts with younger people and colleagues. In addition, she is an outstanding advocate for computational science and served on many community assignments and in many different ways. And of course, also to Cecam, as we saw, but also on committees for Cecam. So I think there's no question that you really deserve this prize. And when I look back into the work of the evaluation committee, I don't want to get into any details, but we had quite a few, I think, excellent nominations. There's no question. But on the other hand, the committee, after a very short time, came to the conclusion there's one person which was sticking out, and that was Giulia Galli. So I think I'm very happy to present this award to you, and I think you now have to come here. And so it's my great pleasure and honor to present to you the 2025 Berni J. Alder Award, Cecam Prize. And I would like to quote from the nomination that you get this prize, and no, that I have to read off, that you get the prize for pioneering contributions to theoretical and computational methods to predict and design electronic and dynamical properties from first principles, broadening the applicability of computational approaches based on quantum mechanical simulations to multiple disciplines, including nanoscience and quantum information science. So in very short, QM simulations where it really matters. Congratulations.
Thank you so much. Thank you. Thank you.
So now the floor is all yours.
All right. Okay.
You can never have enough chocolate, so also.
Thank you so much. We have the oldest computer in the room, I'm sure, and hopefully it will work. That's let's say. Okay, we start with my email. Not good. Sorry. Yeah. Okay, so before I start my talk, I will explain this title, which sounds a little bit strange in a minute, but I would like to thank Cecam for this honor. And this is really a very important award for me, because Cecam has been incredibly important during all of my career. And I gave my first invited talk at Cecam a long time ago. And I also think that Cecam has been and continues to be really very important for our community, bringing together our community and being an advocate for our community. You know, the fact that computational science and simulation, atomistic simulation are highly regarded today in the community, it has not always been the case. And actually, in not that far past, we especially in physics department, sorry to say, we were a little bit a second class citizen, and things are changing, things are becoming different, and our field is recognized more and more, also thanks to institutions like Cecam that have brought together our community. And so I am incredibly honored, I'm very happy, and I'm also very happy to have my name somehow associated to the name of Berni Alder, whom I had the pleasure to meet in when I was working in Livermore. And the reason why I choose this title has to do with the conversation that I will mention in a minute that I had with him during the years. And basically it means, are we really looking at important problems? Are we really pushing us enough to looking at important problems? And so when I was thinking about what to talk about, oh, by the way, how much time do I have? Because not just like 3 hours or.
So according to the program, you have 45 minutes.
Okay, good.
But I would leave a bit time.
Okay, so before at 35, tell me so that okay. So I thought I would talk about liquids and about disordered solids because I wanted to start by telling you also my connection with Berni, and also because first principle molecular dynamics that I learned in Trieste from Karen Farinello when they were doing that has played such an important role in my career. And these are work done with first principle molecular dynamics. So I'll talk a little bit about hydrogen, water, and also some carbon, because I can never give a talk without talking about carbon. So I will do so also today. So one work that we did in Livermore, this is more than 20 years ago, and I think was successful not only for the results of the simulation, but because it changed the way people were thinking about the system, was on hydrogen. And we coupled first principle simulation with the two-phase simulation, which seems simple, but it's not. So you put the two systems, a solid and a liquid, together, and you simulate until one of the two phases take over. It seems very simple, but it's not, because you have to do a lot of technical thinking about how you put this system together. And we look at the melting of hydrogen. And these are the results that we got at the time. This is the temperature as a function of pressure. And those were the points that we simulated, and also the agreement with the experiment that we had. And the reason why this work had an impact is because at the time, all the free energy simulations that were done on hydrogen were just thinking about two states. There was a molecule, and there was a solid, and there was a linear combination of the two states. And instead, by doing a lot of calculation of maximal localized one-year functions, when the work of Nicola and David Vanderbilt was already there, but this was not a common thing to do at the time. And we did a lot of calculation, understanding that actually that curve and that maximum in the melting curve didn't have anything to do really with the sharp transition within atom and molecules, but was a subtle change. And the implications of having that maximum were quite big. And one of the implications was that if there is a maximum, there is a quantum fluid before actually hydrogen become a crystal, which we could never simulate. Nobody has simulated that yet, but this is a prediction. And the formula there is one of the first time that we could, in a very approximate way, evaluate the importance of quantum effects in our simulation. So it was a time at Livermore where we were doing a lot of simulation of nitrogen, and here I only present this one, and also about phase transition. And they had a lot of implication of what they were doing in Livermore. So the management at some point said, why don't you go and talk to somebody who knew how to do simulation before you, Berni Alder. Fair enough, just go talk to Berni. So before I tell you what Berni said, let me say that he didn't mince words, okay, with anybody. He was very direct. So I go talk to Berni Alder, and he says, well, if it were true, it would be interesting. You know, like as a first comment, I was not happy. So I was actually I went on a mission to convince him. And also, you know, I was talking to Berni Alder, not only on simulation, but also on phase transition. You know, he's the father, phase transition in hard field. But I managed to convince him. And so we transitioned from, if it were true, it would be interesting. So if it's true, it's interesting. And at the end, he said, it's interesting. So I'm very proud of that moment after many discussions with him. And we applied this two-phase simulation to several other systems, including carbon, which I will not present right now, and also to one of the obsession of my career, water. And either at the time, it was a very, very crowded and controversial field. And we studied the melting of ice under pressure in addition to other things. And again, by doing a number, by the way, the simulation that we did on hydrogen and those were possible only because were done on the Livermore supercomputer at the time. This simulation, even today, and this is almost 20 years later, by doing all these diffusion coefficients as a function of temperature to understand how the system melts, it would be complicated, even at the PV level. But anyway, we found that, yes, there is a superionic phase when ice melts that were talked about a lot in those days. But it's not how it was originally postulated, that it was like silver iodide, but it's a transition. It's a gradual transition. And ice, for some reason that are not obvious to understand right away, behaves more like lead fluoride. And there is a second order phase transition, not like silver iodide. So as several of my papers on water at the time, the paper was refused by PRL. And so I went to Berni. I went to Berni and I said, of course, Berni was a member of the National Academy of Science. And I said, Berni, would you send a paper for me to the national, to PNAS? So the conversation starts. First, and we went this also back to that many years. So conversation starts. First, Berni says, are you still doing this? And I said, this is not hydrogen. This is water. And he says, well, you know, it's kind of, you know, first principle MD, two-phase simulation. Are you still doing this? And I said, yes, but, you know, it's different. It's, and then this is one of the things that is still, you know, Laura mentioned this, is still true today. So he asked me, why DFT? You never know if you are right. And so I of course, try to tell him there is nothing else that we can really do. It's a model. And, you know, when I remember talking to Berni at the time, I never understood whether he was secretly happy that what they did with the, you know, the correlation energy, you know, the quantum Monte Carlo calculation for the correlation energy is one of the things that made all the calculation of DFT possible, right? So if they didn't do that, and if they didn't fit the energy correlation energy function of RS, forget about DFT today. And or if he was secretly bothered by that, because there was a problem between Berni and DFT. But anyway, and then he said, it's very simple. You can still use MD, so he would not go against MD, but you just need to use quantum Monte Carlo and do the calculation of quantum Monte Carlo. Why DFT? And I tried to convince him that it was not possible. And this is where the title comes from. Berni looks at me and says, you are not brave enough. So it took like 5 minutes. So like, okay. And okay, so to his, so I must say that those few years before, 2005 and 2006, there were two papers, very important papers, one by Jeff Grossman and Lubo Schmitas, and several papers by David Sepperly, where they did propose methods to compute forces with quantum Monte Carlo. And actually, David Sepperly also did a simulation of hydrogen by using a classical Monte Carlo with quantum Monte Carlo. So in a way, Berni was right? There was an indication that we could use forces. So to justify myself, I want to bring out another paper published 2 years ago by Siwan Chen, who is now a postdoc in my group, and Shiwei Zhang at the Flatiron Institute, where they are still trying to make forces and deriving forces for auxiliary field Monte Carlo efficient enough so that we can do molecular dynamics. So Berni was right, but I was not completely wrong either. But anyway, after several discussions, the paper was communicated by Berni Alder, and he accepted that it was interesting enough. And so I feel very proud of that. And he communicated the paper for us. And so regarding the first question, are you still doing this? I will now ask this question for ICE. And the question is, yes, I'm still doing this. And I will like to tell you now about a work that I did in the last year with Ali Hassan Ali and Marta Monti from, where is Marta Monti? There is the advisor of Marta Monti here in the room from Trieste, and Marco also participated in this work. And so here the question, actually the question was brought to us by Ali, and we were talking about ICE, and he said, look, there is actually this incredible controversies where basically people don't understand what happens, when ICE emits light, okay? And so can we study this? So this is a long story, but what we did, we looked at different configuration of disordered ICE. So this is the disordered hexagonal ICE. Defect-free, yet disorder, with vacancy, with ionic defects and other type of defects. And we look at how it absorbs light and how it emits light. And we did this with the time-dependent density functional theory with hybrid functional. And although we did not understand anything really quantitative, qualitatively, we could understand, and I will summarize the results right now, we could understand why experimentalists see different type of property of ICE when they measure at different time scales. So the emission is different at different time scale because there are defects that stay in the system and continue emitting and having an influence. And so let me tell you that the work that we did was made possible by a development that Marco already mentioned, which was the ability to compute the forces in excited states. If we didn't have this, this work would not have been possible. And so we could do, and we can do TDFT with hybrid functional, having states with different spin multiplicity, but this is very important for this work and also others, so that we can do simulation and compute forces in the excited states, and for systems that are quite large. And this is part of the broader effort that Marco mentioned that we did over those years to study excited states of system. And these are also the same technique that we used in recently in two papers that we published with Laura on defects, one on defects in magnesium oxide and the other defects in aluminum nitride. And these papers also contains a attempt at least to compare different methods, some of the methods not exactly the same, but inspired by what Laura was talking about, and the method that comes from the quantum chemistry community and methods that come from our community. Okay. So we have one desire, which is, and I call it work in progress, although it's, it's not exactly work in progress yet, but because we would like to, we are able to compute forces in the excited states. Of course, to make progress, we would like to derive machine learning potential in the excited states. And we have also progress in doing forces with DSC and also adding non-adiabatic couplings. But let me tell you about the results. These three plots took a long time. Please look at them, a long time. And let me tell you just the idea of the, so the line are on the right-hand side of the plot are the onset of the absorption. The reason why there are not full spectra is because it would be very, very long to do. And the line on those lines here at lower energy are what happens when the system emits light. So three important things. The onset of the absorption changes enormously in ice, depending on the defects that you have. These are around 2 eV differences. But the important thing is that because these processes are really fast, by doing the minimization and computing forces, we really could see what happens. So the system absorbs light. There are hydronium and hydroxide formed. We could see where they interact, the formation of a free electron, where they interact with the vacancy, and also maybe because we were lucky, or maybe because these are processes that are very common, we could also see when the system emits light, wrong bonds formed in the hydrogen bonding. And because we saw that, we understood what happens when the system emits light over a very long time scale. And this is a paper that will be coming out soon. So I didn't show you full spectra, and this is a matter of efficiency. We could do that, but it would take a long time. We started this project because we wanted to understand the emission of water. We could not yet do this, and the reason there are problems related to the fact that the configuration of water are not at equilibrium, and are not at equilibrium also in the excited states. We don't know how to do this. And the other problem is nuclear quantum effects. So we studied nuclear quantum effects in water and ice recently with Davide. Maggie Behrens is a student, was a student with Davide Donadio. We understood why actually the gap of water and ice are similar. Although if you look at the energy level and just doing HOMO-LUMO gap, they are different. And this comes from the fact that quantum effects for the absorption in water and ice are quite different. And all the things sum up to make the gap similar. One thing that we don't know how to do are quantum effects on emission spectra. And this is something that we are working on right now. And this is also why I asked this question to Francesco, because I want to think about how people how people are thinking about quantum effects. Then Kurt talked about a realistic system. There is no such thing as a piece of ice. Like, piece of ice needs to sit on something, right? And really, the important environmental problems related to ice are on ice on surfaces. So if you wanted to understand the chemical reaction, you should actually ask yourself, can you see a reaction at surfaces? How do we do that? So this brings me to another story of something that we are very excited right now. And this is, and I tell you first now the story for water, for reason that will become clear in a minute, and then I will go to ice. So question is, I have water or ice on a surface, which is a surface where I can insert a quantum sensor. Can I use the property of the spin defects, meaning how long a spin defect is in a certain state, to understand what I have at the interface and the product of the chemical reaction that I have at the interface, and which properties? So what you can do is to couple the spin qubit dynamics with water self-diffusion and track how the protons move by computing coherence times. This is a lot of words, okay? So I will unpack that sentence. So, okay, so think about a piece of diamond. It will not be exactly a piece of diamond, where you put a sensor, you put ice or water on top, and you want to ask the question, can I understand what's the interface and what happens? So let me just give you the concept. The first concept is that you want to create a sensor, you want to create a qubits, and you do this by looking at the electronic level of a spin defects. Maybe some of you would have heard of the nitrogen vacancy in diamond or defects like this. And the idea is that they can be in superposition states. And then you are optically addressed, you shine light on these defects, and somehow, I'm not explaining exactly how, you create a two-level system, which are the two lamps for the NV. So we have a defect in our material, and then we want to understand the coherence time. And this is taken by Wikipedia. I could have taken this from another paper, but the truth of the matter is that this plot of Wikipedia is still the best, in my opinion. And so I took it from Wikipedia. And so this is telling you that to measure coherence time, you can use a different pulse of light that cause decoherence of the system, then realign it again to form an echo that tells you the time that the defect takes to decohere, to lose its quantum state, okay? And anyway, there is a very nice, so we, in the last 10 years, looked at these properties for a number of systems. One thing we did not do that we are interested in doing is how defects are entangled. By the way, if you don't study entanglement, all the rest is pretty useless, but we think that we will get to study entanglement and that what we do will become useful. But anyway, so, okay, so but let's talk about coherence. So let's think you have a system, you have a spin qubit, and you want to measure coherence. How do you calculate coherence? Coherence is computed with the spin Hamiltonian, the H up there, and then we look at the spin dynamics by looking at the evolution of the density matrix, and we relate the decay of the off-diagonal element of the density matrix with the coherence times that I just showed you, the Wikipedia cartoon, the echo. There is a way of doing this. We use a cluster correlation expansion method, which was actually proposed for the first time in a PRB in 2008. We generalized this method. Nikita, my student, Onizar, generalized this method in 2021 by connecting the different clusters and also using, including avoided crossing, clock transition. And then recently we were able to use a quantum Liouville equation to understand dissipative bath. But the important thing is, if you know the electronic structure of your system, you can set up that Hamiltonian and you can compute the decoherence time. So what is now the model that we are using? The model is pretty classical, except for the qubit. So we have a water in contact with a 2D carbon system that for now doesn't resemble diamond that much. It still looks like graphite, which doesn't even have a gap, but this is what we could do. And it has spin 1, it's like the nitrogen vacancy, but the interaction between the water and carbon is all done with classical molecular dynamics. The reason being that when we started doing finite size scaling, we realized that you need to have at least 15,000 water molecules for tens of nanoseconds to be able to understand what happens. And so there was no way. I hope that, if we are really able to come up with machine learning potential that are really good, there will be a way, but for now, there is no way. And so we do classical molecular dynamics, and then on snapshot of classical molecular dynamics, we do our quantum calculation, and with this code that we develop, and we compute the coherence times. Okay, so what do we do exactly? We actually simplify that Hamiltonian. We have a noise source that we assume comes only from hyperfine interaction. There are other interactions that we discard. We compute an autocorrelation function of the noise and then a correlation function of the central spin with that noise. There are a number of approximation here that I will not talk about. You need a number of approximation to be able to deal with that noise. And also you need a number of approximation to justify that only hyperfine is important. And we could discuss this if you are interested. And so now question, is the spin qubit sensitive to temperature, pressure, water density, strength of the interaction, and the presence of ions? And the answer is yes, it is. Also because if it wasn't, I would not have given the talk. So that's for sure. So these are our results. These are the correlation function that I was telling you about. And if you look at the central plot, it tells you how the correlation time of the qubit is related to temperature. So it increases with temperature. And also it is inversely correlated to the hydrogen bonding time that you can relate to the correlation function. And this is because of motional narrowing. Okay, actually, people smarter than us and more expert in liquid NMR than us would have guessed this, which saved the day, but we didn't, and we did our calculation. And so what happens is that the noise is fluctuating fast enough that your sensor experiences an average interaction that is weaker than it would experience in the absence of diffusion. And this is why there is a slower dephasing. I mean, we computed all that, I'm summarizing. There is a slower dephasing of the sensor due to molecular motion. And because of the slower dephasing, you can actually understand what the properties are. In spite of the fact that the noise of a proton is huge compared to the noise of many other spins. And not only we are sensitive to temperature, but we are sensitive to the water density that changes when you have the water in proximity of the surfaces, the peak over there. And this is our most important result, I feel. These are correlation time as a function of the cation that you have in water. And these are true error bars computed over very long simulation. You see the T2 can distinguish the different cation and can distinguish different concentration. We would be very interested to understand when you plot this as a function of the hydrogen bonding correlation time, if there is a universal curve. We could not do that yet. We need to do many more simulation. We did not do on ions because we don't have potentials. The classical potential that we found were for cations. And if we had magically tomorrow a bunch of machine learned potential for different substrate and different cation, we could look at universal relation. And of course, we are very excited at the idea of doing that. So let's go back to ice. Can we, because we started from ice, right? Can we use a spin defect as a quantum sensor of the property of ice? Answer, no. And the reason is that, at least for the property that we wanted to sense, is that all this works because of diffusion and because of motional narrowing. If you have a static system, it may work. I need to talk to David about that, who's an expert of pre-melting at ice. It may work on a pre-melted ice surface, but it cannot work. And for ice, we first used a semi-classical model for water, but then we went to a full quantum model because we thought maybe zero field splitting is important. You have coherence times that are more than an order of magnitude lower than in water. And those coherence times stay exactly the same within our error bars if you have ions. So you cannot see ions. If you have ice, And why were we so worried about ions? Because if you want to understand chemical reaction, you need to detect OH minus H3O plus. If you don't detect that in ice, you don't detect any chemical reaction. I mean, so that's where we are. Exactly 2 days ago, a paper appeared in PRL where there was an experiment done with diamond, where they used a quantum sensor to actually look at water dissociation. 10 minutes, okay. They looked at water dissociation. So this is much more complicated than what we did. They had an STM where they could inject electrons. They didn't measure T2, they measured an hyperfine, but when I saw this paper, I was so happy. I mean, there are experiments that are being made, right now, and that probably will lead to an ability. By the way, there is no other way to look as of now when you have a water or ice on the surface to really understand what happens at the interface without completely modifying the system. So this would be a big deal. And one of the authors of that paper is one of the father of quantum sensing with NBs. So there are very important people authoring that paper. But anyway, one thing that we are, the reason, one thing that we are trying to do, and actually this is inspired by our collaboration with experimentalists, is not to use diamond, but is to use a 2D system because we want to minimize electrical noise. Let me explain what I mean. If you want to use a sensor, certainly there is so-called magnetic noise, which is the interaction with the protons and the interaction with all the nuclei, right? The spin of the nuclei. But there are also dangling bonds, and these are electrical noise producing. And if you have a 2D system, you may actually get away without electrical noise. We studied the surface of diamonds in a paper that was just submitted a couple of days ago. And one thing that, so by the way, these are much more sophisticated calculations than the one with water. These are all quantum calculations. But to cut a long story short, what we understood is that, yes, there are all the noises that we consider with the spin defect interacting with the nuclei, but there are other sources of noise, this one. Because we can now, with the quantum Liouville equation that I showed you at the beginning, understand the dissipative noise, we could understand the surface hopping. So the fact that there are electrons on the surface due to dangling bonds actually cause decoherence of the NB center. If you have this, in addition to the magnetic noise, your sensitivity goes down quite a bit. And so having a 2D system where you don't have to worry about the termination, and you can hope of having less noise. So the question, are you still doing this, also apply to diamond surfaces. Actually, yes, I'm still doing this. And I started doing diamond surfaces a long time ago here in Lausanne. And this is a work that I did with my friend, Alessandro De Vita. And I went back to this work. By the way, these are the colors chosen by Alessandro. I never liked them. And now, I do like them. But anyway, so I went back so we have an expert in our department, Alex High, in creating diamond membranes. And I went back to him and tried to tell him that if he could graphitize just a little bit the first layer of diamond, then we could put water on that and we could put the sensor in diamond. And he's telling me that it's impossible, but anyway. And as I said, I did this work with Sandro De Vita, and even 7 years later, it's kind of difficult for me to think that he's not there anymore. When I was in Lausanne, we were also with Francesco throwing fullerenes on diamond. Actually, we had very beautiful images that were, you remember in color. I didn't find them, unfortunately. So here are these.
It was a very nice print.
Yeah, I know. I
still have some.
Yeah, I could not find them, but we developed an order and method that we implemented with tie binding molecular dynamics, and we looked at how fullerene of different energies would impact surfaces, and it was a lot of fun. Yeah, exactly. But I know, I did not find them, unfortunately, and and it was a lot of fun also because this paper is when finally the code was working, and as Francesco said, it took a lot of chocolate, and that's. So we are now looking at 2D materials to minimize noise. And we have done a search of 2D materials by coupling the code for the correlation time with AIDA. And this coupling has really allowed us to do a search not only of 2D materials, but the substrate, and it has, right now we also learn how to do this coupling for other searches, and it's going to be great. So we actually did a search not only of the 2D material, but also 2D material with substrate. And Michael Toriyama, a postdoc in my group, derived an analytical model that now allows us to do really prediction fast for these 2D materials. We don't have good defects yet. And, the other thing is that if you want to understand the coherence, you need to know where the nuclei contributed to the coherence are in your sample. And we have made some progress. Abby Pottishman in my group has made some progress in understanding this problem too recently. Okay. So instead of conclusions, I thought I would leave you with some questions, and so, by the way, the question of Berni, this was not a question, it was a statement. You are not brave enough to state with me, right? And, I've answered in different ways over the years of my careers to this question, but I also always thought it's very good question. So let's ask some question to conclude. I thought not very much, but at least I hinted at our method developments, code application. And so what should we do? Still worth writing code? This is a real question. We are experimenting in my group of what happens when you give to ChatGPT certain, for example, Python scripts, not to, but Fortran, absolutely not, because, not an update, of course, but shall we feed equation and algorithm to ChatGPT? Okay. And this is a question that probably also Laura was alluding to and was asking, how much time should we spend on improving or learning functional? Shall we spend more time in developing and applying systematically improvable theories? And of course, quantum chemists always say yes, but it's a valid question. It's not clear. And the other, of course, is a question of, shall we think about theoretical framework to leverage quantum computers? And I don't know, we did some work on quantum computers and we kind of stopped because right now we don't have a lot of new ideas. And there are, all kind of questions about impactful application. In my opinion, one impactful application is about material for sustainable AI, for sure. Because you need to develop something else other than burning all the energy of the data center. And sometimes I ask myself, should we go to completely other domains? We are talking about entanglement. Do you want to do quantum sensor for dark energy? Is it crazy? You want to entangle a system with gravitational wave? And this may sound crazy, but it's not too bad. So I list here the people who did the work recently. I didn't list all my collaborators, and I tried to, by the way, the first three people, they are Eugene and Nikita Onizak and Victor Yu. Nothing, really nothing of what I have shown today of recent time would be there if they hadn't worked at that. And Marta, who was a student in Trieste, a postdoc with Ali and Margaret was a student and now is a postdoc at Livermore. And I leave you with some picture of Berni. And so the picture up there is a picture taken at Berni's 90th birthday at Livermore. And he's sitting close to Malkelos. And when I was in Livermore, first of all, the discussion between Berni, Alder, and Malkelos were always a great lecture, right? Because they were old. But when I was in Livermore, Malkelos announced that the fermion problems was solved. And Berni came in, I still remember, Berni comes in, looks and said, no. And then this gave rise to like months and months of discussion. And anyway, really, I mean it. Listening to those two discussing was a real treat and a real lecture. This is the last time in October 2011, I saw Berni Alder. We had a reunion in Livermore with some of the previous members of my group in Livermore and my group members in Davis. And we invited Berni, of course, at the time of the picture, he had already left, but he came to this reunion and we had a lot of great discussion. And I thought I would put picture of Berni with David Sepperly. I mean, Berni, as I said, he never minced words with anybody. And there was one special person that was above anybody else. And this certainly was David Sepperly. And this is the day Berni received the Medal of Science. And he was lucky that his Medal of Science was won in 2009. I mean, he was not lucky to win, of course, but he was lucky he won with the right president. Thank you very much. And thanks again for the great honor.
For this wonderful day that you have shared with us. Questions? Francesco?
Yeah, it was very interesting the result with relaxation time. But I mean, I left the field of EPR in MR, but a few years ago, they started.
Why? But that's
change.
Yeah.
But it was the challenge a few years ago, to many years ago, was to create EPR. NMR EPR sensor on a surface, so to have, for example, a defect and do to measure the G tensor,
right?
Just
right.
the reaction times. And I think with NMR the signal is too small. I think I don't know. Was more. I think there were effort on that direction also, but EPR is simpler because the spin is much stronger. There are experiments on that because you look to the reaction time. In principle, you can put a magnetic field, complete the G factor of spin defects on a surface.
Yeah.
And that is surface EPR. I don't know if.
Yeah, there are.
It's the experiment that you mentioned.
No, I mean so the difficulty of that experiment, and also what we were trying to do is to do it in the presence of water. Okay.
Yeah,
but yes, there are, and one of the experiments that have been done on that have been done by Natalie De Leon in Princeton, working on samples prepared by Bob Cava there. So there are experiments, and they are not so clear cut in the sense that what you are saying is true. I mean, there are still, problems, and they don't have the same data. I mean, there are still controversy, but there are experiments where they measure G. They measure G.
Easier, you think that is more promising to measure G or the reaction time? What is the different type of information you get? In principle.
I think, based on what I know on experiment, that as of now it is easier to measure T2, but I'm not sure that is true always. I think that now is the relaxation. By the way, I talked of one relaxation time. There are several relaxation time depending on the pulses. That's.
Out of curiosity, in the photochemistry of eyes, have you simulated the hydrogen formation? Probably you mentioned about hydrogen formation.
Oh, the molecule, no. Yeah. No, we are aware that this, yes, that we have not simulated. And I can tell you that this is a process that we will not simulate anytime soon, in my opinion, because of the time scales, in the sense that the formation, there needs to be tunneling that we cannot yet describe, and the hydrogen needs to find it. It's more, yeah, it's difficult, but we are aware that actually one of the referees pointed out that yes, that but we cannot do this, and it may still have an effect on what we see for sure. Yeah, that's.
More questions?
In the back, lots of people.
Yeah. Shy young people in the back.
Okay.
Less shy young person in the middle, scholar.
No, I was thinking of this brave enough, and I always wonder that different scientific communities, are able to somehow organize themselves around great goals. I mean, sometimes it's necessary, and but the experimental particle physicists do this. Astronomers do this. Of course, you do need a James Webb telescope. You need a square kilometer array, and maybe our community doesn't need it. But I keep wondering, if we should maybe try to be brave in that sense and polarize and organize our community towards maybe some flagship goals. It's a very open question.
Yeah, no, it's it's part of the question. What we should do, right? Are we brave enough? Means what is it that really we should be doing to have the highest impact? And in terms of application, in my opinion, our community could pick a couple of really, really important application, right? In terms, instead of saying, I don't know, all of catalysis, pick some problem and identify, we all want to work at this. Or in the solid state, we really want to work at system for low power electronics. And people also in terms of tools, right? How do we really, people have brought together communities of tools, probably not enough, in the sense that we don't have a way of coming together with many tools and also using each other tools. We are still very territorial, right? And there are reasons why people are territorial. People are territorial because they need to push their own things to get their own grants, right? It's not that they are territorial because they are just stupid or something. There has been some convincing of the fund. What you have done here with Marvel is one great examples. There are some examples in the United States of putting together different centers where tools are developed, but a real, for example, connection between the different centers towards the common goal has not happened. And now the OE has decided that they will cancel everything and do something else, which is crazy, but this is another problem, right? So we have a lot of work to do. I'm not quite sure how. Maybe there are some ideas from the back, young people. I don't know. We really need fresh ideas. Yes.
So it's a great talk. So I just want something about order and everything. So our experiment still lots of mission. Center to measure the photon sense, but you may know to manipulate space state everything. Micro
Sure.
So
sure.
Actually, cause measure the static picture can increase the temperature. So that's a problem. But the good thing is for the diamond surface, I think it's hydrophobic. I'm not from chemistry, but I think with certain terminations on the surface, it's hydrophobic. So you propose the 2D system. Did you consider the hydrophobic system on the surface of the Felix?
Yeah, that's a very good question. So the surface it's important question. So the surface that we have chosen there is a hydrophobic surface because we wanted to understand the configuration of the hydrogen bonding, and we didn't want to have yet reactions. We are doing we don't have yet the results to present, but we are trying to understand the difference with hydrophilic surfaces. But instead of using diamond, which is complicated we are using silicon dioxide. So we use the silicon dioxide and we have some hydrophilic surfaces, and we are trying to understand what's the difference. There will be the difference also because water configuration on hydrophobic and hydrophilic surfaces, as you probably know, are quite different. And so we are, so the other thing that I should have mentioned, which is really very important, and I think this is a work that also Laura was involved with, really there is an effort to bring quantum sensing into the field of biology, right? And using sensing also to sense properties of proteins. And there has been a work that I think it's quite important that has come out in Nature a couple of weeks ago or 1 month ago from the University of Chicago, where they show, and I think again that Laura was also involved, that they can use a protein as a part of a protein as a sensor. So I say this because the work is important, but also to say that no matter what you do in biology, you will have to deal with water, right? And so you better understand how you can sense water, otherwise you're not going to go very far.
Yeah, in your second point here on the slide, you say that DFT is a not improvable theory. Maybe I just want to push back a bit on this point.
By the way, I've used DFT all of my life, so it's not that I don't want to speak against DFT. I'm just asking questions, but please go ahead.
Yeah, so I mean, there is stuff we can do to systematically improve, in my opinion. So I mean, of course, there's like a Jacob's ladder, which should in principle give you a systematic improvement, and then you have even better things like the Gerling-Levy perturbation theory.
So I think that the word here is systematically. And so first of all, I have to say that I respect and like very much the person who invented the denomination Jacob ladder. I don't like Jacob ladder at all because it's not a ladder. Okay, and actually I usually in my talk, when I talk about DFT, I use Escher stairs, This is what DFT really is. And I mean, John Perdue is fantastic person, but Jacob ladder, no, please. There is no ladder because it's not, first of all, when you say, I go from LDA, PB, whatever, and then meta GGA, for which property are you doing, your improvement? And also this is not systematic improvement. It's a different level of theory that you can say for a large portion of some, property is working better, but it's not a systematic improvable theory. I don't think so. And I don't want to say that the theory is not systematically improvable. I want to say that the tools that we are using right now do not represent a systematically improvable part of the theory. That's what I want to say. And
more of a small comment on the first one, rather, like if people don't learn how to encode their own equations and algorithms onto the multi-core or big machine supercomputers of today using language which is more unambiguous than English, and there's not that much science left to do if you can just load it all into ChatGPT.
So again, maybe I should have explained better my questions. I am not asking this question because I think that the answer is yes. Okay. I'm asking this question because I think that we should think about that. And thanks for your comment, and I'm very glad that you think that way. But I'm just I had a long conversation this morning with Michele Ceriotti about this question, and Michele is not here now. He had another things to go to in Sweden, but and we were trying to, he was telling me his experience and the experience of his students to really try to understand how to, use ChatGPT to write code. And there are some surprisingly good and surprisingly bad things that come out of it. So I really I have no idea about the answer to this question. I think that at some point, at least, we will use a part of this for our codes. But the fact of writing codes, like me and Francesco was doing in the old days, is to learn the logic of how to solve a problem. And this is something that we need to know how to do. Even if ChatGPT knows how to do it, we need to know how to do it, for sure.
There's another question there. General question. So we were saying that we will never know if the DFT population is correct or not. But I don't know if we should always trust the experimental result.
Yeah.
If you go to a database, if you go to the NIST database, and if you check the experimental data there, you will see maybe the experiment was performed 100 years ago. If I want to do the benchmark.
Yeah, that's a very important question, because your question basically is how do we validate our results, right? Is the experiment, do we have experiments that we can trust and that we can use to validate our results? And in some cases, we do not. If we had at least some cases where Laura and others do an exact calculation, right? Maybe we could, on the same system, benchmark DFT. This is a huge problem, a problem of validation. And by the way, especially on these quantum sensing and on one of the experiments that Marco mentioned about intersystem crossing, I spent a fair amount of time going to my friend experimentalists, telling them this is not quite right. They don't believe me, but sometimes questioning experiment is not a bad thing either. That's I'm sorry, I don't have a better answer to this.
Okay. We're running fashionably late, but I don't want to break the conversation too soon. Maybe I can just remind everybody in the room that we are lucky enough to have an opportunity to keep interacting with Giulia and all the speakers of today's mini symposium at an aperitif that will start in the hall in a while. So if you don't mind too much, I think
sure, let's go.
Giulia again.
Thank you.
I would like to invite Andrea to
Stefan.
Stefan, I'm sorry.
Yes. To close this beautiful day, very beautiful day, we started with the welcome from the EPFL president and the Cecam president. A very nice word about Cecam from everyone. So I'm very proud to be the Cecam director, very honored, and a big responsibility, of course. And then top scientist delivering lectures. And finally, the prize. Thank you very much, Kurt, for taking care of this task and this duty. And then finally, the lecture of Giulia who started exactly with one of the main messages we try to deliver at Cecam. Are we brave enough? So this gave me an idea to probably organize a strategic working group, also including younger ones, for what we are calling continuously the grand challenges. The grand challenges is probably the new mantra for society-driven, for community-driven efforts. And also, the end of your talk is exactly the end of my welcome to people coming to Lausanne for workshops. Don't close your lectures with conclusion, more with challenges. Were questions, but as you said, were not questions, were challenges, because the answer was not, were not rhetoric questions. I thank already everyone for being here. I must thank our staff, Cornelia, Bogdan, and Elodie, who are here in person, and also those who are not here, Sabrina, Natalie, and Carol, who are making our life quite easy, but particularly they are taking care of organizing in a very, very efficient way all of our flagship program. Not only here, I'm seeing Francesco's in other places, in Lugano, they are very effective also helping people in other places in Switzerland to organize workshops within our flagship program. So again, just a couple of minutes more to suffer before the aperitif, because I leave the stage to Stefan, and then we go for having the apero together and to celebrate again Professor Giulia Galli. Thank you again for being here.
I think I don't want to add much more than what Andrea has already said, but I would like to say that I know Giulia already as a graduate student a long time ago. She was also for me admiring person. I really enjoy and also very, very happy about her life and scientific trajectory on overall stages in Europe and in the US. And I would like to say that her talk reminds me, or is a kind of a statement where we stand in the simulation of complex systems. And there are more questions than answers. And as I mentioned to Giulia already, I think we have a lot of problems left for the young generation to solve on time scale, on length scale, on energy scale, on this and that. And maybe in 20 years, nobody writes anymore a code the way we have written it, you know, line by line. Maybe you talk to your computer and your computer tells you what to do. But I think understanding complex systems, simulating complex systems on all levels is a remaining problem and a remaining challenge to us and also to the next generation. And with this, I would like to maybe close this wonderful Cecam event and invite you to the aperitif next door.